Hello and welcome to another session in the Mind Grid. And today we are looking back at a topic on PTP accuracy. And the topic today is going to be asymmetry in networks. So let's start with the slight introduction to PTP protocol. And before we actually talk about asymmetry and how it impacts the accuracy, let's just look at what PTP protocol looks like. The PTP is a protocol for synchronizing different parts of the network. And the way this protocol works is that you have a grandmaster that has an accurate sense of time, and somehow with some messaging or communication between grandmaster and the intelligent end device, which can pass on this timing from the grandmaster into that intelligent device. Um, so the way this happens is that there are several messages that are seen. We will focus on the important ones from our discussion standpoint. The first message in them is called sync message. And as you can see it here, the sync message is the message that is being sent at a certain time and received at some other time by the target device. And then sometimes there may be a follow-up message, but otherwise the sync message can contain the complete information, so there may be a follow-up message. Now, after that, there is a message called delay request that is asked by the target device and sent to the master. The master responds with a delay response, and that completes this process. Now, the way the PTP protocol works is that you measure 4 different times: T1, which is when the master sent the sync message; T2, when the end device receives this message; and then T3, when the end device sends the delay request; and T4, when the master receives the delay request. And then obviously all these are sent back to the target device as well. So you have T1, T2, T3, and T4. Now the way this calculation theory works is that you calculate 2 different values, A and B, and A is the total perceived delay between the message being sent um, and the message being received by the intelligent device, which is T1 minus T2, or sorry, T2 minus T1. But keep in mind that T2 minus T1 contains 2 values. One is the delay, which is how long it took, and the second is the offset, which is how much these 2 clocks are misaligned with each other. Because there's always a misalignment when you start with synchronization. You have to assume that the clocks are misaligned to begin with. So you have to factor that in. So the first variable A is delay plus offset. And then if you look at the other side, which is when you send the delay request, that measurement, which is B, is really T2, T4 minus T3, and that is delay minus offset. And so with these 2 variables, you'll be able to compute the delay and the offset by doing these calculations, A plus B by 2 and A minus B by 2. So with that at the back of our head, now let's look into what the asymmetry in the PTP networks is and how it can impact your calculations, your accuracy, and so on. So the goal may be in PTP networks to synchronize so that you have, tens of nanoseconds of error in your accuracy um, in a PTP, well-tuned PTP network. Now, as I've talked about in my previous video on PTP, that the devices in the middle of the network, they may be intelligent PTP-aware devices like transparent clocks and boundary clocks, but there are other cases where the setup of the network is such that you just have an L2 switch in the middle, and if you have just an L2 switch in the middle, then there may be other problems, and asymmetry comes about in those cases. And so in this case, let's just assume there's the grandmaster and the intelligent electronic device at the end is receiving some of this timing through an L2 switch. So the possibilities are, there are various possibilities for delay asymmetry. And as you saw here, that PTP assumed that the delay in this path, forward path and the backward path, they're all the same. See, this calculation based on the fact that this is not delay 1 and delay 2, it's just delay. And so we assume a symmetry, and that's how we are able to use this protocol and determine that. So in case this forward delay is not the same as this backward delay towards grandmaster, then there is going to be a problem. So the basic problems here are that, you know, there is static asymmetry and dynamic asymmetry. In the static asymmetry, one of the variables is speed mismatch. So if, let's say, you connect to grandmaster at gigabit, and then you connect the intelligent electronic device at 100 Mbps. So there is inherent conversion from 1 gig to 100 Mbps. And whenever that let's say it happens in this switch here, whenever that conversion happens, then there is a store and forward happening in this switch. Because the switches check CRC, etc. If you look at, if I have a picture. So there is a store and forward delay in these switches. And when frames come in, they actually stored in each direction before they're transmitted on. So now if you look at this, that when the frames are stored here in the switch and transmitted, they're being stored at either a gigabit, which is the rate at which it's coming in, or when you go from here, maybe it's being transmitted into the switch at 100 Mbps. So it takes a longer time for the packet to arrive. So there is going to be an inherent asymmetry in this case, and we'll talk about that in a more detail in a little bit. The other thing is path length mismatch. So we are assuming that these are switched networks, but what if these are routed networks? And if these are routed networks, then it's possible that, for example, if you have PTP routers in the middle with or without boundary clock, um, the ones that have the boundary clock support or transparent clock support, they're able to accommodate the fact that there are these errors and the storage and buffering of these packets. They're able to accommodate for these things, right? But the switches that are not aware of PTP, they are not able to. And if there is delays in these, like in this case, there was this delay here, like just like a boundary clock or transparent clock was able to use that, a regular switch is not able to. And so these errors, which are the time that is spent within any switch, or storage time or buffering time that is happening inside a non-PTP switch, that can introduce an asymmetry. So here, going back to this again, then there is speed mismatch and there's path length mismatch. So path length may happen because if this is a router network, going in this direction, you may take one path, and going backwards, you may take a completely different path, and there may be some delay asymmetry, which PTP is not going to know about. So these two are problems that you will have to deal with. There also is dynamic asymmetry, which is if there is congestion. If there's congestion in one direction, then there's going to be buffering in that direction. And in the other direction, maybe some different kind of congestion or no congestion, and that'll introduce a delay asymmetry. So again, just remember that asymmetry is not something PTP likes. The delays and offsets are assumed to be similar in these equations, and it's going to impact your algorithm and accuracy. So you have to make sure that the paths are designed in a symmetric fashion so that the accuracy remains high. So now the congestion obviously is not going to be all the time. It may be something that comes and goes, and it has a certain impact in a more dynamic way. And there may be approaches to handle or filter out the variations, if you will, of the measurement of T1, T2, T3, T4, and accordingly the delays and offset, you may be able to filter out the noise in that. So these are the various ways in which this impacts us. And now let's just take a quick example of like a realistic example of how the delays can impact us. So for example, if you in PTP protocol, if you have a sync message that is 86 bytes long and is being transmitted at gigabits, then the delay to buffer this packet is 0.688 microseconds. And then the delay request packet, which is being sent at size of 86 bytes, and it has been transmitted 100 megabits. So at 100 megabits the delay is 6.88 microseconds. Now, right there, you can see that the delay asymmetry comes into play because you have taken so much longer to buffer up a packet that's coming from a 100 megabit network. And because of that reason, the thing is that you have to encounter asymmetry. And then if you calculate the net delay value, which is a plus b by 2, then you'll come up with 3.784 as the perceived delay. So now what has happened is that in this forward going direction in which the actual delay was only 0.68, the PTP protocol has now somehow calculated 3.784 microseconds. And in the reverse going direction where the delay was actually 6.88 microseconds, it has calculated the delay to be 3.784. So in a way, if you just focus on the forward going direction, instead of 0.6, we have somehow computed 3.7. And so that's not good. We have to correct for it, but we have to know that this is happening. And so you have to come up with ways of detecting how the network topology is constructed and be able to measure these asymmetries in your PTP network. So in a sense, those are the important variables that you'll have to deal with when you're dealing with PTP protocol. And that's all I wanted to cover in this video. Hopefully you liked the video. And if you have comments, please share with me or share the video and subscribe to my channel. And I thank you for watching. I'll catch you in another video. Until then, take care. Bye-bye.